Here's an approximate graph of pendulum data, or pendulum information, the actual data points. Well, I'll mark them as we get to them. We had a maximum pendulum length of 7 blocks. Now we measured pendulum length by concrete blocks up and down the wall. So the maximum length of a certain pendulum was 7 blocks long. Okay, now this isn't actual data from an actual pendulum. This is demonstration. You should have your own data from the actual pendulum, and you can graph it accordingly. I chose to mark the x-axis in units of 8, or make the x-axis the labeled part of the x-axis 8 units long, where x is in blocks. And I could have put that down here. So I could say x scale is in blocks, and for y, the scale is in seconds. Now the actual data was 1 minute count of the pendulum, so this isn't actually raw data that's being graphed. We infer from the number of counts in a minute how long each count took, and that's what we're graphing here. So maybe I should label the graph just for clarity for the video. Everybody knew what I was talking about in class, of course. Well, nobody ever really does. Actually, many did. I think people understood what was being done in class because we have a really good class here. The graph shows pendulum period, because the period is the time for a complete oscillation, versus length, the period being measured in seconds, the length being measured in block widths. And a block width, incidentally, is 8 inches, give or take a fairly small uncertainty. Okay, so we mark this off. Since we have a maximum length of 7, it's convenient to mark this in units of 8, because then we can subdivide the interval from 0 to 8 and get 4. I kind of missed it with my line there, but there's 4. And then subdivide from 0 to 4 to get 2, subdivide from 0 to 2 to get 1, subdivide from 0 to 1 to get 0.5. So here are pretty good consistent units on the x-axis, okay? And we can do that using compass and straight edge. We're not going to do a graph this big with this little compass, but we understand how that's done. Now you can ignore a lot of this writing over here. We'll come back to it. Some of it has directly to do with this graph, some of it doesn't. We determined from the counts that when the length was 7, the period was 1.1 seconds. And when the length was half that, because what we did was we kept folding the pendulum string in half to get a pendulum of half the maximum length and then half of that length, half the maximum length gave us a period of about, I don't remember what the number was, it was something a little below 0.825, maybe it was 0.8 seconds. It gave us a point here. And then at half that, we had a period around 0.5 seconds or a little less. And that gave us a point here to go with the point we had for maximum length, which was here. Then we sketched a smooth curve. It's not a perfect smooth curve. Among other things, as we'll probably discover later, the curve really starts tangent to the y-axis and then curves. From this graph, we could then predict what the period would be for any length with reasonable certainty. Now over here in scaling the y, we had a 1.1, and we constructed, we cut this in half to get a period of 0.55 at the halfway point. We could construct that in half and get a period of 0.275, and take half of that, and so forth, and mark the axis in those units. and there's really no more accurate choice, but those numbers aren't particularly convenient. They're not particularly easy to deal with. So we'd probably make a reasonable modification on that. But there's our graph. Now we try to determine what the y factor is for this graph. Okay, so when x doubles, well, y increases from this to this. Let's see, if y had doubled, it would be here. This looks like a factor of about 1.7. In other words, the y value for this point is 1.7 times the y value for this point. Now, if we were to double this y value, we'd be way up here, and this looks like it's more like 1.4. But if so, this would tend to indicate, if this was our actual graph based on the pendulum behavior, and it isn't, but if it was, this would tend to indicate that maybe we don't have a power function relationship here. Okay. Okay, we're going to stop there, and then we're going to talk about what we did with the numbers and the symbols over here, and some of the procedures we asked you to use.